in these 45 points, we have 5 short answer. And that's it. Five short answer. With these 5 short answer, there are 2 multi-part questions. Right? That means A, B, C, D. And everybody's favorite question that they like to ask. There is no extra credit available on this exam. So keep that in mind as you do your exam and as you peruse through it. It is 1 page back and front, and you get 60 minutes. Now, I see there's a lot of questions about percent yield. So we'll cover that first. So, percent yield. For percent yield, the equation is the actual mass divided by the theoretical. And that is times 100. And this equals your percent yield. Now, the important thing to remember here, and especially with it being on the exam, the one that you get from STOIC is the theoretical. So whatever you get from STOIC is the theoretical. The one that you get that is usually given on exams is the actual mass. Now, if you recall from the lab that you all did, right, you calculated the theoretical yield from 2 different masses. So that's what we're also going to be doing here. We're going to run through a problem, and we will figure out the theoretical yield, and we'll also calculate we'll then give you an actual mass, and we'll do the calculation from there. So let's do an example. Example 1. Let's say you have this equation. Right? N2 plus H2 yields NH3. Let's say if you combine 14.7 grams of nitrogen gas and 3.6 grams of hydrogen gas, what mass of NH3 should you get? What limits this reaction? All right, let's go over this, right? This looks pretty complicated. It isn't, but we can go over it. Whenever you're given this sort of problem, right, and on the exam, your first step should be balance. Now, the reason your first step is balancing is because you really can't do anything else until you balance, right? The balancing needs to be, because you use your balancing for the mole ratio, So we need to go and do that first. So if we balance, we see that we get a 3 here and a 2 here, and it's all said and good. Now, step 2. This is where we start getting into some actual math here. We need to convert. In this case, we'll start with N2 mass to NH3 mass. Now you can do the other one first, like you could do H2. It doesn't matter what order you do it in, but essentially you'll do both. So let's do this one first. So we have, let's put this guy over here for right now. So we have 14.7 grams of N2. Now, I don't want grams of N2, so we need to go ahead and convert this to moles of N2. Now, we know that in every 28.02 grams, this number, before you go rushing to the questions, this number here is the molar mass of N2. And we know that by definition of a molar mass, that this is equal to 1 mole N2. Right? We know that by definition. Now, we go ahead and multiply this. I don't want moles of N2, right? Moles of N2 right now is kind of useless to me. So we need to convert this to moles of NH3. To do this, we need to use the mole ratio. So we know that, according to my equation up here, that for every 1 mole of NH3, I get 2 moles of, for every 1 mole of N2, I get 2 moles of NH3. I get this 1 from here, and I get this 2 from there. Zoom back in. 2 moles NH3, 3, and then 1 mole of N2. Now, you may ask, am I done here? Should we give ourselves a pat on the back? You could be done here, but let's just finish this last step, just so that way we're in grams of NH3, so it's easy to compare which one's larger and smaller. So our last step is to multiply. So if we've already used the molar mass of NH3, we've used the mole ratio. The last step, you may be saying it in your head right now, is to again use molar mass. But do we use molar mass of N2? No. We use the molar mass of NH3. Now, that, of course, is 17.04 grams of NH3, because this here is the molar mass of NH3. Now, all we do, multiply the top by the top, bottom by the bottom, and then divide. Let's zoom out here just so we can see the whole ball game. So we can retranslate this into 14.7 times 1 times 2 times 17.04, all divided by 28.02 times 1 times 1. Now, if you've been following along, just like how we've got it here, writing out your units, which is very important, right? These cancel here, these cancel here, and these cancel here. So we're left with grams of NH3. So all I do at this point is I put it into my handy-dandy calculator. 14.7 times 1 times 2 times 17.04 divided by 28.02 times 1 times 1. And I get a mass of, wrong color, mass of 17.639 grams of NH3. Here, we needed 3 sig figs because our starting measurement was in 3 sig figs. Now, you may be saying, all right, great. We're done. We've done a 3-step. This is a great day, right? And I'd say, yes, you are half done. Half done, because we've only done half of this problem. Our next step, 3, is to convert the H2 mass to NH3 mass. All right. So, according to my values up here, which, by the way, all this information up here would be given to you on the exam, right? I'm not going to ask you to come up with values of this on your own, right? These are going to be given. But it says I'm starting here. I'm just going to retroactively add a 0 there. 3.60 grams of H2. Okay, I think I'm in bright pink. So 3.60 grams of H2. Right, that's our start, that's our given. Now, we've got to get rid of grams of H2. So, just like in the last one we did, this one we start with molar mass. But instead of molar mass of NH3 or N2, we use the molar mass of H2. And that's for every 1 mole H2. Now, if we follow our same kind of pattern here, our next step is to use the mole ratio. Now, to do this again, we look up here at our balanced chemical equation. We see that for every 3 moles of H2, which again comes from the 3 in the equation, we get 2 moles NH3. So far, so good. Right, we're on the right track. This is great. But our last step, of course, is to multiply by 1 mole on the bottom. And that's for every 17.04 grams NH3. So that way, we're ending in grams of what we want. So if I go through this, we go bang, 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 and bang. And I'm left with grams of NH3 at the end, which is exactly what we need to compare these two values. So if I was to put this into my calculator, I would do 3.60 times 1 times 2 times 17.04 divided by 2.02 times 3 times 1. So again, pull out the calculator. We go ahead and do 3.60 times 1 times 2 times 17.04 divided by the quantity 2.02 times 3 times 1. And I get equal to 20.2 grams of NH3. All right. Are we done, right? Can you give yourself a little pat on the back right now? We can't. Not yet. You can give yourself a pat on the back here in a minute. But first, we've got to figure out what limits our reaction? And get this, whatever limits your reaction is your theoretical yield, or results in your theoretical yield. So step 4 is identify the limiting reactant. And again, to do this, the smallest answer comes from the limiting reactant. So here, if I compare our two answers that we got, this shows that our limiting reactant is N2. So this is great, right? In this case, N2 limits the reaction. Great. All's good and now is done, right? But let's add one more dimension of difficulty here. Example 2, using the theoretical yield from example 1, consider that the actual yield is what's it, 17.9 is 13.3 grams of NH3. What is the percent yield? All right, now we're kind of tasked with finding out what this percent yield sort of thing is. Now, we went over the equation at the start, but just so that way we're all familiar with it again, percent yield is equal to actual over theoretical times 100%. So if we look back, our theoretical yield comes from the lowest answer we got. So our theoretical yield in this case, laser, is 17.9 grams of NH3. And our actual comes from the question, 13.3. So we have 13.3 divided by, what was it, 17.9? 17.9. These are grams of NH3, grams of NH3 times 100. So we just put this into our handy dandy calculator, 13.3 divided by 17.9, and we get a percent yield of 74.3%, which is our final answer. So again, let's point this out one more time. This 17.9 came from, we'll use green, right? This 17.9 came from here, right? Came from right there. And this 13.3, on the other hand, comes from there. It's our given. and job's good, right? Job's good, job's done. The actual yield will be given to you on the exam in that problem. And all you need to use that actual yield for is percent yield, right? We've done all this math before, right? We did all these steps before we actually used that actual yield. So, right, that was a long problem. Everything is, good and everything's right. Notice everything that I've done here, right? The big things being, right, noting your units everywhere, right? Noting your units everywhere is a pretty important part, right? Noting units here, noting units here, noting units here, right? If you can't overdo your units, right? Even here, I noted my units, right? You can't overdo your units. Sig flags do apply to that percent yield. There's a question here of, do we need to know combustion, decomposition, right? For all that, like identifying the names of these reactions, and looking at the exam right now, you don't. There's a question here where it asks for the mass of something, dinitrogen tetraoxide, that contained 1 million of nitrogen atoms, right? Will this be on the exam? No, it will not be. It contained 1 million nitrogen atoms. What's the mass of the overall thing? And no, that one won't be on there. However, one that would be on here is one that uses Avogadro's number. So let me just section off this big problem. Let's get to Avogadro's number. Now, Avogadro's number. Avogadro's number is the number of particles, atoms, molecules in 1 mole of anything. Now, you may be asking, well, what is this number, right? It's a magical number, right? The number is 6.022 times 10 raised to the 23rd power. So 6.022 times 10 to the 23rd is the number of moles in anything. Sorry, number of particles in 1 mole of anything. So let's do an example. Let's say I have 2.5 moles of, let's say, FeCl3. And I want to figure out the number of particles. Right, what's the number of particles of NH3? Or FeCl3. So when I'm setting up this equation, I know that we've got 2.5 moles FeCl3. Now, I know that in every 1 mole of FeCl3, we have 6.022 times 10 to the 23rd. That would be particles of FeCl3. And if we take a look here, these two cancel out. So I'm left with 2.5 times 6.022 times 10 to the 23rd. So I'm going to go ahead and put this into my calculator. 2.5 times 6.022 times 10 to the 23rd. And I get 1.5 times 10 to the 24th particles of FeCl3. Job's good. All right, go ahead and give yourself a little pat on the back. Right, you've done it, and I'm proud of you. Let's do another one. But this time, instead of going from moles to particles, let's go from particles to moles. Example 4. Let's say I have 1.37 times 10 to the 22nd molecules of SF6. And I want to get to moles. SF6. All right. So to do this, we just go in reverse. 1.37 times 10 to the 22nd molecules of SF6. 6 times, I might actually make this smaller. Times, I know that for every 6.022 times 10 to the 23rd molecules of SF6, I get 1 mole of SF6. So we've just done it in reverse. Again, these cancel out. So I'm left with my equation, and when you're putting this into your calculator, it's very important to make sure you use parentheses. 1.37 times 10 to the 22nd, end parentheses, divided by parentheses, 6.022 times 10 to the 23rd. Again, the parentheses here are so important. If you don't use parentheses, your entire answer is going to be thrown off. So we need to use parentheses here. I know it sounds redundant, right? Why doesn't the calculator just do it the right way? It's because of PEMDAS, right? Your scientific calculators do follow PEMDAS. So I have 1.37, the quantity 1.37 times 10 to the 22nd, sorry, divided by 6.022 times 10. That one's to the 23rd. And I get this is equal to 0.0227 moles of, what was it? SF6. And that is our final answer. Now, Last note of Avogadro's number before we move into another question. You only use 6.022 times 10 to the 23rd if the question asks for particles, atoms, or molecules. Asks, I should further clarify, asks or starts with. So you only use 6.022 times 10 to the 23rd if the question asks or starts with particles, atoms, or molecules. So, right, this you would use for, right, if you're going from grams to particles to grams, moles to particles, and vice versa. And if you're going and doing stoic, right, grams of some substance A to particles of B. And again, vice versa. You do not use for, keep it in red, grams to moles, grams to gram conversions, or mole to mole conversions. So again, if you notice here, right, the important part here is that each one of these on the green side has some flavor of particles or of molecules or of atoms, right? But the ones on the right, the ones in red, don't. They only have grams and moles. That's it. So if your question doesn't ask anything about particles or grams or anything like that, you don't use it. Makes it easy. Will hydrates be on this exam? No. Do we need to know combustion? No. The limiting reactant always will be your theoretical yield. Sorry, we're doing cleanup questions right now from our previous one. See, for example, in this one gave us the smallest amount. That's our theoretical yield. You thought it was 6.02. The more precise number is 6.022. You'll be able to get away with either one on this exam. Stick with the units that they give you in the exam. So if it uses molecules, use molecules. If it uses atoms, use atoms, right? Don't try to interchange those on the exam. But for the sake of 6.022, they are interchangeable. I'm going to take a quick drink of the coffee I've got right here. We'll get back to questions here in a moment. All right. Coffee filled. Let's do some more questions. I saw a question towards the beginning I want to hit on first. Is there a easy way to remember kind of the steps of this? There's somewhat of an easy way, but it's mostly just, unfortunately, memory. The best way how to remember kind of what step to do next is the following. Let's do another example, and I'll point it out along the way. Example, what's it? Example 5. Let's say I have this equation. The combustion of methane, we've got C2, or CH4 plus O2 yields H2O plus CO2. Now, let's say I start with 14 grams of oxygen gas. How many moles of CH4 do I need to use up all those 14 grams of oxygen gas? All right, amazing question. Let's dive on in. Again, your first step for this, just like how we did with example 1, balance. How many of you are balancing in your head right now? You should have gotten something along the lines of 2 and another 2. Right? So now, if we just make sure we go over this, we got one carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 2 oxygens here, and 2 oxygens there. Job's good. All right, I'll give us a little check mark. Heck, I'll even give us a smiley face. If you say my smiley faces look like crap, you fail immediately. Our second step is to do that stoich. Now, if the question that was here, right, how do we know what steps to kind of do everything in? It's a great question, right? Is there like a mnemonic or something that helps me remember? And unfortunately, there isn't. But here I started with, what was it again? 14 grams of oxygen gas. When I multiply this, whatever unit I have here I've got grams of O2. I need that same unit down here. Right? Those units must be the same. And the only thing that I know that we can kind of relate grams of O2 to moles, which is what we want, is the molar mass of O2, which in this case is 32 grams, 16 plus 16. And I know that's every 1 mole of O2. Now, again, you may be asking, are we done? No, not yet. Here it's asking how many moles of CH4 we need. So, to do moles of CH4, again, I need the same unit that I had here, right? Those both need to be the same. Not 1 mole. Now, again, I look at my chemical equation, I have a 2 here for every 1 mole of O2. Or sorry, of CH4, apologies. Now, all I do is I put it into my handy dandy calculator gun. 14 divided by the quantity 32 times 2. And I get 0.22 moles of CH4. Or in other words, when you need to go from grams of compound A to moles of compound B, you do your given times 1 over the molar mass of given times your mole ratio. And that will give you your answer. So again, those are the very general steps. But what if instead I say I want 0.517 moles of H2O, how many grams of CH4 do I need? Amazing question, right? It's a question of the ages, right? If I want 0.517 moles of H2O, how many grams of CH4 do I need? Now, in this case, of course, your first step should be balancing, but I've given this to you balanced. Your second step, we'll do it in pink, is to go from moles of A. And whenever I say moles of A, that's your given, or grams of A, that's your given, to moles of B to grams of A. So let's begin. 0.517 moles H2O. Now, I'll multiply. If I've got moles of H2 here, what do I need here? If you said moles of H2O, you'd be correct. It shows, according to my chemical equation, I need 2 moles of H2O, and that's for every 1 mole of CH4. Now, I know that it's in for every 1 mole of CH4 because, again, that's what we get from our balanced chemical equation. Now, we finalize this by, for every 1 mole of CH4, we get 17.04 grams of CH4. Oh, apologies, 16.04. 16.04? 16.05, my apologies. Grams of CH4, with 16.05, of course, being the molar mass. Now, we finalize. Again, grab your handy-dandy calculator, 0.517. I'm sorry, the quantity, 5.17, 0.517 times 16.05 divided by 2. So this means in order to get 5.5 moles of water, I need 4.14 grams of CH4. So we can reduce this down to what it is step by step for those people who are asking for a step by step sort of deal. for every equation where we need to go from moles of A to grams of B, you follow these steps. You do your given times your mole ratio times 1 mole of your want on bottom times your molar mass in grams of want. Right? That's it for everything, right? Right. For those two steppers, those are the two variations that, those are two of the couple variations that you can see. Now, let's say instead I wanted to go from moles of A to particles of B. This was a little more tricky, but it's not as tricky as you might think. We don't need our molar mass here. You do your given times the mole ratio times, for every 1 mole of want, you get 6.022 times 10 to the 23rd particles of B. Let's do an example of that one. We'll actually draw the other version you could get given your particles of A, 2 moles of A. This, you do your given. Oh my goodness me. Times 6.022 times 10 to the 23rd over 1 mole. And then finally, your mole ratio to end it off. So if you notice here, these two things, right, this guy here and this guy here, are just mirrors of each other. Right, these are the same here and these are the same here. They're just here in a mirror. That's it. So Avogadro's is never, it can be only one step, but it's not always. Like there's a question here on the exam, right, that I'm pulling from right now, right? It says, if this reaction created blank molecules of hydrochloric acid, how many grams of blank did the reaction create? So, right, it's not always just one step. Can be, but we'll do an example where you go to moles, and we'll do an example where you go to grams from particles, and we'll do another example from up here as well. Oh, wrong one. EX7. So we've got these two equations. Let's dive into them. Let's say I start with 17.7 grams of CH4. Let's just say we start with that. I want to go to particles. Actually, not in this case, it wouldn't be particles, it'd be moles, or sorry, molecules of not of CH4, apologies, of, let's say, H2O. molecules of H2O. All right. Right. This is a great example, right? It's kind of pulling from the exam actually a little bit. Step 1, balance. Right, we've done that. Yippee. Step 2, we'll do it in beige. Now we do our stoich. We have 17.7 grams of CH4. We multiply this. Your first step here is utilizing that molar mass. 16.05 grams of CH4. That's for every 1 mole of CH4. Next, you use your mole ratio. I know that for every 1 mole of CH4, I get 2 moles of H2O. I further know that for every 1 mole of H2O, I get 6.022 times 10 to the 23rd molecules of H2O. So if I'm looking at my steps for going from grams of A to molecules of B, it's very similar to what we just saw at the top. You use your given times your molar mass of given over 1 mole times your mole ratio times 1 mole of want, and that's under 6.022 times 10 to the 23rd molecules. And guess what? If you want to go in the reverse direction, you just flip it. You just do it in reverse, right? It's so cool. Sorry, I'm nerding out over. But if we go from molecules of A to grams of B, we start with our given times, but instead of it being on the top this time, it's on the bottom. 6.022 times 10 to the 23rd, and that's under 1 mole of given times your mole ratio times, we know that in every 1 mole of given, we get the molar mass in grams. And that's it. Job's good and done. Let's finish up the beige one here. We'll do one that's in the reverse direction. And I think we've hit most of these topics that you can encounter using Avogadro's number. So again, I just put into my handy dandy calculator here. We got 17.7 times 6.022. Oh, sorry. Times 10 to the 23rd divided by 16.05 times 1 times 1. And I get this is equal to 6.64 times 10 to the 23rd molecules of H2O. Let's do one in reverse. Getting tired of writing out this whole equation. I'm gonna just copy it. So let's say we've got this. Example 8. Let's say I have 1.35 times 10 to the 25 molecules of CO2. And I want to go to grams of O2. So again, you're going to notice that we follow these same steps that we get here, just here. So let's do it. I've got 1.35 times 10 to the 25 molecules CO2 times, we know that in every 6.022 times 10 to the 23rd molecules CO2, I get 1 mole of CO2. I further know that according to my mole ratio here, I know that we get for every 2 moles, oh, apologies, 1 mole, I get 2 moles O2. I further know that in every 1 mole of O2, I get 32.00 grams of O2. Now, we just put it in our calculator. Ooh, sorry. I get 1.35 times 10 to the 25 times 2 times 32.00 divided by 6.022 times 10 to the 23rd. It's going to be a big, big number. What's this, 3 sig figs? I get 1,430 grams of O2. So here we needed 3 sig figs because our starting number had 3 sig figs. One question came in a little bit ago that I missed. We'll leave this here, just right here. When, for questions asking about limiting reactants, the final answer should always be in grams, right? That's what your final answer should be, right? I care more about how many grams something has versus how many moles it has. Naming on the test, you need to know chemical names. We give you all the formulas, but for the naming portion of it, there is no naming here, just going over formulas. Some equations you only need to balance for the stoich that's on here. That's correct. Naming is not a component of the exam. Some equations, will some equations already be balanced? No, we ain't that nice, but you got to balance some of them. Can you give us a short question, or short answer question example? All that we've been doing, the examples 1 through 8 have all been short answer examples. So that is hopefully helpful there. There's no like writing out, if that's more what you're asking. All these short answers are all math based. How do you determine how many significant figures should be in your final answer? Great question. Let's showcase it with this one. The reason why we'll use, I don't know, beige. The reason why this has 3 sig figs is because this has 3 sig figs. We always go based on our measurement. Or in other words, you always go by your given. You determine significant figures based on your given. Will there be naming? No. To check your work, Can you take your answer and do it backwards? Yep, absolutely. You just take your backwards and flip it. So, can you explain how you got the 6.64 times 10 to the 23rd? Because when I calculated it, it didn't match. Sure. For this one, I assume you're talking about example 7. When I put this into my calculator, I did, Jesus, what was it? 17.7 times 6.022 times 10 to the 23rd divided by 16.05. I'll redo it just in case. Yeah, I still get 6.64 times 10 to the 23rd. I would check your putting it into the calculator. What do you mean formulas? Like just name two formula? I mean stuff like I give you all the equations that you need. Or you may be asked if I give you a cation and an anion just to do your crisscrossing. Right? That's like 2 points on this exam. Can you go over how to set up the rest? Sure, we definitely can. All right, so we've done grams to molecules, molecules to grams, moles to particles, particles to moles, moles of A to grams of B. We could do a, can add this just up here. Oh, wrong color. If we want to go from grams of A to moles of B, we do our given times, we do the molar mass of our given, and that's over 1 mole, or that's under 1 mole of our given, times, we know that we then are do our mole ratio. We did a gram to gram one up top. So I'll just showcase the kind of step-by-steps you take here. If you want to go from grams of A to grams of B, we do our given times, we use our molar mass of given, and that's under 1 mole of given, times our mole ratio, times, we know that in every 1 mole of our want, we get the molar mass in grams of want. So that's just how you do your gram to gram. For mole to mole, that one's probably the simplest of them all. You just use your mole ratio. But we will showcase it just in case. Perfect. There's a nice little spot here. It's just about the size you need. Mole of A to mole of B. You do your given times your mole ratio. For the person that pointed out the small error that was in this problem, you are absolutely correct. I missed out multiplying by this 2 up here. So the actual answer for example 7 is 1.33 times 10 to the 24. Thanks for pointing that out. We've answered this one. We've answered this one. We've answered this one. Will we be given a problem in words and write the chemical equation on our own? Let me just confirm on these two exams that I've got here, because there are two versions for tomorrow. For each one, the equation will be given. So you don't need to write the equation from words. You're welcome. Is there more of a certain type of question on the exam, like more gram to gram questions or more gram to molecule questions? It's actually a good spread of, like, it's a nice even spread, right? There's usually, it looks like there's like 1 mole to mole, there's like 1 mole to gram or gram to mole, mole to particle, more particle to mole, and then one limiting reactance equation with, or question with a limiting, sorry, with a percent yield at the end. And yes, this note sheet will be posted on Schoology as well as the YouTube video of this thing. Now, currently we still have 20 minutes on the clock, and I've answered every question that has been posed here. We're gonna leave the questions open for just a moment before I do another example, just to kind of reinforce everything that we've been showcasing here. But before we do that example, I'm going to take a drink of water and coffee. Hey, that was just the example I was about to do. All right. Example 9. Let's say I have this equation. To H2O. Let's say I start with and I start with if H2, how many grams of H2O do I get? What limits the reaction? All right. So, great question. Amazing stuff. Think to yourselves, what should our first step be here? You said balance the equation. You would be correct. Give yourselves a little round of applause. You did a good job, and I'm proud of you. Balancing the equations, the first little bit here. So if I do a 2 here and a 2 there, job's good. Now, let's just start here with our 10.1 grams of O2. Our first step is we multiply. with the molar mass on bottom, 32.0 grams of O2. That's for every 1 mole of O2. I further know that for every 1 mole of O2, I get 2 moles of H2O. I finally know that for every 1 mole of H2O, I get 18.02 grams of H2O. Now, I go ahead and put this into my handy dandy calculator. 10.1 times 2 times 18.02 divided by 32 times 1 times 1. I get 11.8 grams of H2O. Now I do my second one. I have how many grams? 4.3 grams of H2 times. I know that in every 2.02 grams of H2, I get 1 mole of H2. I further know that for every 2 moles of H2, I get 2 moles of H2O. Finally, I know that in every 1 mole of H2O, I get 18.02 grams of H2O. Again, put this into my handy dandy calculator. We get 4.3 times 2 times 18.02 divided by 2.02 times 2. And this means I get 38.3 grams of H2O. So now I compare. Which one is the lowest? Or let me rephrase, answer isn't the best term here. This is our theoretical yield because it is smallest. So if I continue on, let's say the actual of H2O is, let's say, what is the percent yield? The actual will always be given. The answer to this first question, if it was just this first question, would be 11.8 grams of H2O. O2 limits the reaction. You are correct. Now, let's say for this question, right, question, I guess technically example 10, if the actual yield was 3.75 grams, but you expected to get 11.8 grams, we just put this into our limiting reactor, apologies, our percent yield equation. times it by 100, this would mean our percent yield is 31.8%. Kind of a crappy percent yield, but if that's what we get, that's what we get. The next question I see that was asked is, what does, if something says something is in excess, what does that mean? If something is in excess, that means that we have a unlimited amount of it. Or in other words, you can ignore it, right? If we have an unlimited amount of it, that means we just get enough for it. Is writing O2 limits the reaction 18.0 to 11.8 grams of O2 and 11.8. Yeah, it's the same thing. You're just writing it a different way. All righty. With that, I think that's where we're going to call it for tonight. I hope this session was helpful for everyone. I hope everybody does well for the first iteration of the exam that is coming in less than 12 hours. If you have any further questions, I'll probably be up for the next time. Is it 9:20? Probably for the next 2-ish hours. Feel free to send me an email. How early can I come in to ask questions prior to first hour tomorrow? I can do I'll be there probably by 7. Can you zoom out so those in MRS's class can screenshot? Absolutely. We will do this will be the first page here. I think it might be better if I flip it, maybe. So that way y'all can zoom in. We'll let people screenshot this. You can do a little thumbs up. I will scroll down. I will scroll down again. Job's good. Again, I hope everybody found this helpful. I'm planning to be in 295A hopefully by 7. So if you have questions, feel free to come on by then. We're going to go ahead and stop the recording. For those of you joining us on the recording, thank you again for watching. And we'll see you at DePaul College Prep.